So today we're going to present the fourth paper in our ECE 493 class, Design Trade-offs for TAL CMP of On-Chip Networks by James Balfour and Willie Daly, the NVIDIA man. I'm Anthony,
I'm Tanuja.
and we're excited to go over the paper. Okay, so first off, let's go over the motivation of the paper. Why did these people spend the time to write it? So essentially, the point of this paper is to try to do a complete network performance analysis for chip multiprocessors. So what's interesting about this paper is it extends previous works by not only considering theoretically, but actually considering a physical design and layout using an actual practical 65 nanometer process, and then seeing based on this actual process what is the best on-chip network for these kind of chip multiprocessors. So first off, what is a CMP? So really quickly, it's basically just a multi-core processor. So you should be familiar with commercials. CMPs, like for example, a four-core processor, and then you have a bunch of cores, and they have L1 cache, and then they're communicating with a shared L2 cache. Pretty standard stuff. And then the CPU cores require a large amount of communications, which obviously could be done point to point, but we know from this course that the better method. So this paper is an investigation to different network on chip topologies to try and figure out which is the best. So obviously, which is the best, you need some sort of metric. So the metrics of analysis is basically considering two areas, area efficiency and energy efficiency. Because in silicon, area efficiency is important because how large your chip is affects how expensive it is to actually manufacture something, and then energy efficiency is also important, really how expensive it is to use the topology, and then also it's the amount of heat generated, which affects the scale you can actually use the topology. And then both of these parameters are then related to the latency and capacity, throughput of different packets and different packets routing and different traffic distributions. And then to try and figure out for different latencies and capacities, how much energy or area do you have to give up to achieve a certain metric. Um, so the way they modeled the area and energy of these systems, first I'll go over the latency and capacity. So these are kind of all theoretical analysis and that they then try to implement. So these are kind of the goal network configurations. And there's a lot of formulas, and then I recommend going to the paper to understand how they derive these formulas, but I'll just give you a quick summary. You have this T0 term, which basically refers to the latency of the message. So when you send a message, how long do you expect the message to be routed through the whole system and received? And the capacity, which is basically how many messages you can send, which is obviously related to the bandwidth. So it's about 2 times this bandwidth parameter. So we can see here these are the different topologies they are comparing in this paper. We can see that the CMesh X2 has the lowest latency and highest capacity. So it has like this high bandwidth term, and then it has a low latency term over here. And then we have mesh topology, which has the highest latency and lowest capacity, which is 17.8 and 3072. So even before we consider, importantly, even before we consider area energy capacity, you would imagine that in the metric of how fast you're able to route all the messages, CMesh X2 will win. And I guess the big idea of this paper, or what this paper is trying to investigate, is to see if this high throughput comes with some sort of energy or area inefficiencies or not. So now let's go into the power and dissipation area model. So this uses a 65 nanometer process, and then I'm not going to go through all these different parameters, but they have a series of different parameters that affect how big these transistors are that we're using, how much energy they're going to do, which mainly relates to their different capacitance and obviously their leakage current. And then we have kind of, I believe they define some sort of average activity factor based on each topology, and then they use that to kind of find the amount of power distribution because you have the leakage currents, which kind of dominates a lot of this energy dissipation, and also switching, which dominates as well. Those are the two main terms that we look at. Anyways, they then use these models to actually construct the actual system. So we have here a simple example of an SMP model. So I won't go over all the 3 sections, but they basically split up the way they do this on each module on the SMP into 3 different sections, which is the input, the switch, and the output. So the input is what comes from a different processor, the switch is the routing, and the output is if it's going to, like if it's setting further along if it wants to send it to a different core um, for processing. And then it goes through doing the energy and area for each of these 3 sections, which I encourage you guys to read. And then there's also the channel model, which is the channel connecting these different processor tiles. And then that is obviously also going to affect power and time delay, as well as area. And then over long distances, the paper isn't very explicit, but it does specify that they will need repeaters as needed. I'm not entirely sure what that means, but they basically have these repeaters connecting the modules, these tiles processors, and that also incurs some area and power loss.
So let's go over some of the network topologies and the routing algorithms that were used in this paper. So there were 5 that were used to evaluate the performance. So the first one was mesh and mesh XU. So that was a variant of the mesh with 2 networks repeated. So mesh is pretty straightforward and simple. Each tile connects to each router. That's how the routing takes place. And second network, kind of we get the first network kind of repeated with increased wiring and area utilization. And we'll kind of go over into how each network, what functionality each network handles later on in the presentation. So this is deadlock avoidant by its nature. So our next one is the torus topology. So it's very similar to the last one that we looked at, except that the ends are kind of looped back in, forming like a torus-like shape here. It's a more folded topology we're seeing here, and the routing is the dimension order routing that's used in the paper. And interdimension deadlock is avoided using partitioning. We'll move on to the next one, which is concentrated mesh C-mesh. So this is an important topology in the paper. It's a reduced mesh. So the mesh is like a reduced to a 4 radix mesh. So we can see each router has 4 ports as opposed to 1 port each. It decreases the average hop count because there's less routers in the network. And there's also an additional express channel path there. So along the router, we can see. So if there's more than one hop in the path, it can take the express pathway through the router and it's deadlock free. So again, similar to the last one we saw, the mesh we saw before, this can be implemented with 2 networks in the same or in similar amount of space to improve more performance. So again, we'll look at that more down in later slides. So this is a fat tree topology, and it's an instance of a folded class network. Please refer to the appropriate paper regarding more information about this. And it uses nearest common ancestor routing. And this is another topology that's looked at in the paper for analysis, and it's an instance of the generalized fat tree, and bandwidth decreases towards the root. And the routing algorithm is similar to that of the F tree, and say a packet reaches the root while routing up the tree, it's randomly forwarded to one of its descendants. And then deadlock, so interdimension deadlock is avoided by partitioning each ring and promoting packets into reserved kind of sets of virtual channels. That's how the paper explained it. So we'll look at the simulation and setup of the experiment here. So for the simulation, the cycle-accurate interconnection network simulator was used. So that's kind of what was used to measure the 2 key metrics here, which are area and energy efficiency that was previously explained in this presentation. So area efficiency is a product of load completion time and chip area, and energy efficiency is a product of completion time and energy expended. And data path width, number and partitioning for channels, fit buffer depths, and placement of routers among tiles were tuned to each topologies to get the best performance. And a bit more simulation setup. So simulation involved every process performing a fixed number of transactions and measuring time to completion. I believe it was more than 1,000 messages that happened. And packets entering the network during startup with little queuing delay had no effect in the overall completion time because there was a large number of messages in the network that passed through the network during the simulation time. A variety of traffic patterns were used to avoid any biasing towards a particular network topology. So some of the patterns that were used were bit reverse, nearest neighbor, tornado, and uniform random. A closed loop system is used so where each sender and receiver may have a number of packets in flight, and it better represents a CMP that's used in the industry. So let's look at the results that came out of this simulation. So looking at the first 2 graphs, A and B, in figure 10 provided in the paper, performance and efficiency. So in figure A, the graph A, we see the workload completion time, and C mesh obviously has the least here when scaled, and mesh with 2 networks takes the longest time. And looking at C mesh here, we see that using different traffic patterns, we get kind of similar performances. Nothing really quite dominates it. And looking at graph B, where we see the area performance here, again, C mesh with 2 networks takes the win here. And we see that tiles across all the topologies takes up a fair bit of the area budget here. and in CMesh, routers take up the next amount of place, and where it kind of performs the best is reduction in channels. So compared to F3, it's a significant reduction in channels, the pair that's needed for channels in CMesh. So that's kind of how CMesh kind of gains its power from by reducing the amount of pair used for channels. And now we're going to look at the two other graphs of data. So on graph C, we see the network power dissipation. So here we see CMesh and T-Tree kind of winning the power dissipation battle. So looking at CMesh here, it's somewhat evenly distributed in terms of power dissipation. Memory taking a little less, but channel and switch are kind of even. And looking at the rest of the data points, we see that channel power kind of dominates the power consumption, which is interesting because in the previous slide we saw that channel area dominated the area consumption as well. So now looking at graph D here, relative efficiency, CMesh has almost double the efficiency as the worst performing topology here, which is mesh with two networks. So again, that's reflected in both area and energy here. So yeah, we can move on to the next point here. So now the paper looks at adding a second network and seeing the performance improvements or the effects of that. So before that, we're going to look at the two variants of second networks that are kind of introduced. So two combinations. One is heterogeneous and one's the homogeneous network combination. So the heterogeneous architecture, that's where one subnetwork transfers or transports the shorter packets, and the other one transports longer packets. In the homogeneous one, instead of splitting it up between the packet based on packet lengths, it splits it up based on reads and writes. So one handles reads and writes and their requests, and one handles reads and its requests, and the other handles the writes and the corresponding requests for that. So the first one we discussed, which is heterogeneous, performs much worse, just because it splits up based on the length. So since there's a even or a equal kind of number of long and short packets in the network, the network that's in charge of handling the longer packets would go through a heavier or would have to endure a heavier load. So just because that unbalance of the network traffic, the heterogeneous one performs much worse than the homogeneous one. But now considering that the effect on chip area is pretty much negligible because the second network kind of sits on already used space, so it doesn't have much of an effect. Performance increase introduced from the second network more than offsets the power dissipation increase. So in general, it's more efficient to have a second network especially with homogeneous. So now we're going to look at the findings of the paper. So in general, CMesh with two networks proved to be the best. And increasing channel capacity improved area and energy efficiency, and replicating networks also improved performance, especially using homogeneous. And Anthony, do you want to explain the last point here?
Yep, and we know that now that CMesh X2, as the paper was through the simulations, proved to have the best relative efficiency. The paper makes the claim that this is because it has a larger channel capacity, and this is kind of what propels it to be more efficient. And then it makes the claim that topologies that have a higher throughput are more efficient. However, I think a next step or a question I ask is for the paper is at what point is this saturated or limited? Can this increased channel capacity proceed ad infinitum to improved area and energy efficiency? If there is some sort of trade-off with channel capacity, if there's some sort of technical limit, I think that's an interesting question that the paper can leave me with.
So that'll be all. Thank you.
Thank you.